Moment of inertia. If you recall, the mass of an object is the measure of its inertia, and an object's inertia is how resistant it is to a change in its motion. A greater mass requires a greater force to accelerate it. Previously, we've related these ideas to objects in translational motion. Here's Newton's second law of translational motion, just replacing net force with translational force, and acceleration with translational acceleration. A certain amount of force is also required in order to accelerate a rotating object about its axis. This force depends on the mass of the object, but also on how the mass is distributed around the axis of rotation. What does this mean? Well, this board could have a number of different axes of rotation. Its axis of rotation could go this way, meaning the board would rotate in this direction. Or its rotation axis could go this way, so that the board rotates in this direction. In the first case, the board has a large rotation radius, r, and in the second case, it has a small rotation radius. The angular equivalent of mass is called the moment of inertia, I. So the moment of inertia tells us how resistant an object is to a change in its angular motion. I equals m times r squared for a particle of mass m at a distance r from the rotation axis. So the moment of inertia depends on both the mass and how the mass is distributed around the rotation axis. Moment of inertia is in units of mass times units of distance squared, kilograms times meters squared. Let's consider my model airplane to be a particle of mass m moving counterclockwise on a circular path around an axis of rotation. If the airplane's engine creates a translational force, the airplane will be accelerated translationally. We already know the relationship between these thanks to Newton's second law. The torque on the airplane produced by the translational force is equal to the magnitude of that force times the distance from the airplane to the rotation axis, r. r is the radius of the circle of motion. Substituting in Newton's second law, we get this expression for the torque. We found previously that translational and angular acceleration are related in this way by the radius r. Substituting in this expression for translational acceleration gives us this expression. M times r squared is equal to the moment of inertia for an object. So we see that torque is equal to moment of inertia times angular acceleration. This is similar in form to Newton's second law for translational motion, so we call it Newton's second law for rotational motion. In reality, the model airplane is a rigid body made up of many particles. As the airplane moves around the rotation axis, each particle obeys Newton's second law for rotational motion. Each particle has its own torque as the body moves about the axis of rotation. Each particle has the same value for angular acceleration, since each is part of a rigid body. The torque on the entire rigid body is equal to the sum of the torques on the particles. The torque on the entire rigid body is also equal to its moment of inertia times its angular acceleration. This must mean that the moments of inertia of all of the particles add up to be the total moment of inertia for the body. This is therefore Newton's second law for rotational motion for a rigid body. Rigid bodies of different shapes have slightly different expressions for their total moments of inertia. This is due to the fact that each shape has a slightly different distribution of mass around the rotation axis. In the examples shown, capital M is the total mass of the object. Capital R and capital L are shown in the diagrams.